Welcome, everyone. It's my great pleasure this evening to welcome you to the Gallagher Lecture. My name is Kristen Bates, and I'm the Dean of the Faculty of Science. I'm excited to be here with you tonight. We are glad you've joined us for this wonderful presentation. While I'm not new to science, I am new to the University of Calgary. One of the most exciting things about being here is building relationships with others who love science as much as I do. Calgary is a city based on science. Our success and their success are intertwined, and it's a vibrant community that truly is invested in the success of the University of Calgary and our students. Opportunities to come together and talk about fascinating science topics like this one, the evolution of our planet, is just an amazing opportunity for all of us to explore our environment and think about the land we live on. And though we cannot be together in person, it is still important to think about the land we are physically on and who have shared it with us. We are broadcasting from Calgary, which is located on the traditional territories of the people of the Treaty 7 region in southern Alberta, which includes the Blackfoot Confederacy, comprising the Siksika, the Piikani, and the Gani First Nations, as well as the Tsuut'ina First Nation, the Stoney Dakota, including the Chiniki, Bearspaw, and Wesley First Nations. The city of Calgary is also home to the Métis Nation of Alberta, Region 3. And the university is situated on the land adjacent to where the Bow River meets the Elbow River. And that is the traditional Blackfoot name of this place is Mokisina, which we now call the city of Calgary. The Gallagher Colloquium series continues to highlight speakers who share a passion for science, scientific research, and exploration. I'd like to take a moment to recognize the Gallagher family for making this series possible. It is through their generosity and vision for deep connections between the university and the community. Their support allows us to promote and build public awareness of science and scientific research, and helps us understand why science is fundamental and important, not only to our lives, but to the world around us. And just a few housekeeping announcements before we start. I want to remind everyone we are recording today's session and we'll post the video on the Faculty of Science website. I encourage you to check out our website, science.ucalgary.ca, for event listings and video updates. Again, thank you for joining us this evening. I hope you enjoyed tonight's presentation, and I hope to one day meet all of you in person. And now I'd like to welcome Dr. Ben Tutulo from the Department of Geoscience to introduce our guest. Please enjoy tonight's presentation.
Thank you very much, Kristen. I am Ben Tutulo, and I'm an associate professor in the Department of Geoscience in the Faculty of Science and the lead for the Gallagher Colloquium series. It's my pleasure tonight to introduce Dr. Robert Hazen, senior scientist from the Carnegie Institution for Science, as our speaker. Dr. Hazen is senior scientist at Carnegie Institute of Science and the Robinson Professor of Earth Science Emeritus at George Mason University. He received his degrees in geology from MIT and Harvard. He has authored more than 450 articles and 25 books on science, history, and music. His recent book, The Story of Earth, was a finalist in the Royal Society and the Phi Beta Kappa science book competitions. As a fun fact, it was this book, which I first read during my PhD studies and have read at least 2 times since, that first got me thinking about research questions surrounding the coevolution of Earth and life over Earth's history. These questions are now a major component of my research program today. Throughout his career, Dr. Hazen has received numerous awards, including the 2021 IMA International Mineralogical Association Medal, the 2016 Roebling Medal of the Mineralogical Society of America, and the 2012 Virginia Outstanding Faculty Award. In 2020, he was elected foreign member of the Russian National Academy of Sciences, and the biomineral Hazenite was named in his honor. In October 2016, Hazen retired from a 40-year career as a professional trumpeter, during which he performed with numerous ensembles, including the Metropolitan Opera, the Royal Ballet, and the National Symphony. Since 2008, Dr. Hazen and his colleagues have explored mineral evolution and mineral ecology, new approaches that exploit large and growing mineral data resources to understand the coevolution of the geosphere and the biosphere. His presentation tonight, How Life and Rocks Co-Evolve, the 4.5-billion-year story of Earth, will offer us a glimpse into these novel approaches. Please join me in welcoming Dr. Hazen.
Dean Bates, Professor Tutelo, the Gallagher family, colleagues and friends who have tuned in today. I am so honored to be able to be part of this Gallagher lecture series and to talk to you about the coevolution of Earth and life. Now, the subtitle of this talk was the 4.5-billion-year story of Earth, but what I really think the subtitle should be is Harnessing the Power of Mineral Informatics. And some of you are going to say, wait, I didn't sign up for a mineral lecture. What's this all about? And I hope you'll bear with me because you'll see the connection. And I really want to emphasize how important minerals are to all of us. They provide the essential raw materials for technology and agriculture. Indeed, all life depends on minerals. Minerals preserve a record of planetary history, including biological evolution. Minerals have laid a foundation for solid state chemistry and physics, discoveries of the periodic table, for example, and crystal structures and X-ray diffraction. That's all from mineralogy. And the thing that got me into minerals so many years ago is they're just astonishingly diverse. They're amongst the most beautiful of all natural objects. But there's something else, and this is where mineral informatics come in. Mineral specimens have incredible information-rich attributes of structure and composition and shape and color and size and all sorts of things. Every specimen is a time capsule just waiting to be opened. So what do I want to do today? The outline, there's three basic things. I want to review what is the official International Mineralogical Association mineral classification system, which is based on physics and chemistry. I want to propose a complementary evolutionary system of mineral classification based on changes through more than 4.5 billion years of Earth history. And the way this connects to the lecture is in the process, we're going to introduce opportunities offered by this incredible age of mineral informatics. For example, in exploring the coevolution of Earth and life. So think about it. What are the objectives of a mineral classification system? In fact, what are the objectives of any classification system? Well, first and foremost, it's communication. We need to be able to organize natural objects so that we can talk about them. They can be unambiguously described and named, and you know what I'm talking about, and I know what you're talking about. But there's a second very important part of classification systems. Ideally, they play a central role in the discovery and articulation of successful scientific theories. And in that context, you can have multiple valid classification schemes, each one addressing a different theory or a different aspect of nature. So let's talk about the IMA, the International Mineralogical Association official classification system. A mineral is defined as a natural occurring solid, and a mineral species, that's a technical term, it has a chemical composition defined by its major elements, something like SiO2 is quartz. And each mineral species has an idealized crystal structure. And every unique combination of a composition and a crystal structure is a species. And there are about 5,700 as of today, I think it was 5,741 approved mineral species. About 100 new ones get approved every year. That's what the IMA does. This scheme goes all the way back to 1850 when American mineralogist James Dwight Dana issued his third edition of the System of Mineralogy, Chemical Properties and Physical Properties. Now there's a consequence of this. If you say it's naturally occurring, it has an n-member composition that's idealized and an idealized structure, what you're basically saying is that you're defining minerals with the minimum possible bits of information. The minimum amount of information needed to distinguish quartz from diamond, from emerald, from any other mineral species. But here's my argument. If we want to understand the coevolution of Earth and life, then we need a new classification system that incorporates changes in minerals through deep time. And by deep time, I mean 4.5+ billion years of Earth history. So why propose a different classification system? The first reason is simply that the IMA system does not incorporate the parameter of time. Think about Earth's evolution. It started in a nebula where it gradually accumulated through gravitational clumping. Early Earth was a hellish place with lava lakes and bombarded by asteroids, not much life there. You had about 2.5 billion years ago, the emergence of life that actually could produce oxygen, and that changed Earth dramatically. And then there were periods of glaciation, snowball Earth they're called, where the entire Earth was covered with ice or snow. And now we have the last few 100 million years where we have a terrestrial biosphere, a lush green planet with all sorts of life forms. Now, every planet is a dynamic system, and the histories are recorded in minerals. They're the only tangible things that survive for 4 billion years. The evolutionary system of mineral classification has the potential to inform theories of planetary origins and evolution, and that includes the origin and evolution of life. Okay, a second reason to propose a new classification system, and this is a little more esoteric, I admit, and that's because a natural kind needs to be thought of in classification systems. This is an old concept. It goes back to Aristotle, where a natural kind represents a genuine division in nature that is, in a sense, it's something that's independent of human conventions and interests and actions. In the IMA system, we have idealized chemistry and idealized structure, which is not a natural thing. That's an invention of the human mind. But there are in nature certain natural kinds, and the periodic table is what many people point to. Each different chemical element has a unique integral number of protons. Carbon is element 6. If you have 6 protons, you're carbon. If you're carbon, you have 6 protons, and it's different from 5 and it's different from 7, and every chemical element has its own unique number. So these seem to be natural kinds, independent of anything that humans might invent. Thing is, idealized IMA mineral species are not natural kinds, but a new system that incorporates the kind of messy history of minerals, all the information contained in minerals, could be based on natural kinds. And I'm going to develop that concept through this lecture. And finally, and I think most importantly, an evolutionary system of mineralogy offers new opportunities for really fundamental discoveries. Things like, how does life arise? How does it emerge from non-living worlds? How did life on Earth evolve over 4 billion years? It's minerals that are going to tell you that, because that's what preserves that history. Are we alone in the cosmos? Even questions like that, minerals could really play a key role. And here's the point. The primary tangible evidence we have for the earliest processes in the solar system, and that includes this idea of the origin of life and the evolution of life, is contained in information-rich rocks and minerals. I say again, each specimen is a time capsule. It's just waiting to be opened to be discovered. And the key to understanding the coevolution of Earth and life is the emerging field of mineral evolution. So I want to spend some time talking about mineral evolution. This idea was presented in a paper in 2008 with a bunch of colleagues. And this is really a 3-part story. So here's part 1. This is 2008, 2009, when this idea was first released in a very qualitative form. So what do we mean by mineral evolution? It's basically the study of the changing diversity and distribution of minerals as a consequence of evolving physical, chemical, and ultimately biological processes in a planetary system. So we're looking at changes over time in the diversity of minerals. There's how many different kinds of minerals there are, the relative abundance of those minerals, the compositional ranges of minerals that includes trace and minor elements, for example. Even the sizes and shapes of minerals, these change systematically through billions of years of Earth history. We focus exclusively on the near surface environment in our studies. And the reason is that's what's accessible to study on Earth's surface. It's what's most likely to be observed when we study other planets and moons. It's also where you have direct interaction of rocks with biology. Now, you could extend mineral evolution to the mantle or even to the center of Earth and the core, but this is where we have most of the information, and this is what we've been focusing on. Okay, so deep breath. I have to make a comment on the word evolution, which some biologists have criticized this, saying you can't use the word evolution and minerals in the same sentence. But I want to remind you that the word evolution has several meanings, and it's been used often in the earth sciences. Almost 100 years ago, Norman Bowen talked about the evolution of the igneous rocks, and we talked about evolution of planets and evolution of meteorites and so forth and so on. So I think it's perfectly legit that way. There's also an implication of complexification. If we look at the biosphere, we see going from simple one-celled organisms to more complex and more complex ecosystems. So that's implied by mineral evolution as well. And also this idea of congruency, that is, each stage of mineral evolution follows logically from the prior stages. Okay, but I don't mean this. Minerals do not evolve by Darwinian evolution. So erase that from your mind and we'll move on. So here's the key idea. Here's the soundbite. New minerals form through a combination of chemical, physical, and ultimately biological processes. Planets generate those environments. And what we see are 10 mineral evolution stages of Earth that span the last 4.5 billion years. So let's look at those stages. Actually, there's a stage 0. This is before Earth ever formed, before our solar system. These are stardust grains, grains formed in the envelopes of old stars. The envelopes were cooling. They were rich in carbon and silicon and oxygen and nitrogen and some other elements. And so you form stardust grains. Those early 20 or so different mineral phases found in stardust contain 12 different chemical elements, all of them produced abundantly in stars. And if you ask the question, it's basically how do we get from 20 minerals with 12 essential elements before Earth formed to what we see today, more than 5,700 minerals with 72 different essential elements. That's mineral evolution, 10 stages. Stage 1 is the primary chondrite meteor minerals. These are minerals that formed in the cooling solar nebula, and there are about 90 different species. They're preserved in little droplets called chondrules. Stage 2 is when you start getting formation of planetesimals, what we now see as asteroids. And you have not only the primary minerals that form by igneous processes, but you have minerals formed through heating, through water interactions, also minerals formed by impacting. So that takes us up to about 300 mineral species. And we think that's probably about where we come in stage 3 when we talk about the formation of a planet. If the planet is dry, like the moon or Mercury, we think this may be the end point, about those 300 mineral species, the same ones that fall to Earth in meteorites all the time. But if you have a wet planet, like Earth or early Mars, you can get a lot of additional minerals, up to about 450 different species. And we think this is probably the way Mars is today, about 450 different mineral species. And that may be the end point. So Mars got about as far as stage 3. Earth is much larger, and therefore it has additional melting events. You can melt basalt, which is the black rock covering most of the ocean floor. And when you do that, you produce a magma that's richer in the element silicon and lots of other rare elements. This gives you granites. It gives you something called pegmatites, lots of beautiful rare minerals, up to about 1,000 mineral species altogether, just by these processes. And Earth has another trick up her sleeve. She has plate tectonics, and millions of cubic kilometers of the upper mantle and the crust get reworked. They interact with water and aqueous fluids. They dissolve and reprecipitate minerals. You get new modes of volcanism. You get new kinds of metal deposits with lots of interesting minerals, economically important minerals. You also get mountain building and the formation of high pressure and high temperature minerals of various kinds. So this gets us up to about 3,000 different mineral species. Stages 1 through 5 gives us about 3,000 species that form purely by chemical and physical processes on Earth. But I just told you we've got more than 5,700 mineral species on Earth today. So where do they come from? And the answer is life. Life forms minerals. And this is kind of intriguing because the origin of life depended on minerals. Many different roles have been described. Minerals are catalysts to make organic molecules. Minerals are reactants. They actually participate in making those molecules. Minerals can be templates, sorting and selecting and concentrating molecules on their surface. Minerals can protect delicate molecules from degradation. And you can also have scaffolds that build larger and larger and larger molecular structures that may have been key roles in the origin of life. But by the same token, once life emerged, life created the origin of many new minerals. So let's go on to stage 6. Well, stage 6 really doesn't have a lot of new mineral species. These are the earliest forms of microbes. They're called chemolithoautotrophs. They're actually microbes that eat rocks or get their energy from rocks. They reprecipitate minerals, but they don't make a lot of new mineral species as far as we're concerned. But the punctuation event, the great surge in mineral species, was when life learned how to make oxygen. The oxygen went into the atmosphere. The atmosphere essentially reacted with the rocks at Earth's surface, creating thousands of new minerals. And many of these are the most beautiful minerals in museums. For example, copper minerals. About 2/3 of all the known copper minerals wouldn't have formed before there was oxygen in the atmosphere. And those are the beautiful blue and green minerals that you probably have seen. 90% of uranium minerals just simply cannot form without oxygen. You need to oxidize the uranium in order to make these beautiful minerals. And hundreds of other minerals as well from various elements that are sensitive to oxygen. They change when they are exposed to oxygen. So this creates many new minerals. That's stage 7. Stage 8, a long period of time during which the ocean became gradually more oxygenated from just the surface all the way down to the deepest depths of the ocean over about a billion-year period. That's stage 8. Not a lot of new mineral species, we don't think. And there also weren't many new species during stage 9, that's snowball Earth, a period when there were global glaciations. Some people suggest that ice and snow covered everything from the poles to the equator. So the major mineral at Earth's surface was ice, that is H2O in the ice structure. That's a mineral species. And finally, we come to stage 10, that's Phanerozoic biomineralization, with all the new species formed because of life on land, new clay minerals, new biominerals, such an interesting array of minerals being formed, reefs and bones and teeth and shells and coal with hundreds of mineral species, and decaying plants like cactuses forming even more new minerals. And I have to tell you one story about biomineralization, just because it's so astonishing what life can do. Consider the Trilobite. This was a crustacean that lived in the seas hundreds of millions of years ago, and they often had compound eyes, often with hundreds of individual lenses. And each of these lenses is a single crystal of the mineral calcite. That's calcium carbonate. Well, calcite's clear, so that's a good thing for a lens. The trouble is that blue light and red light bend differently, so everything is out of focus. Calcite makes a lousy lens unless you play a trick, and that is every so often for a calcium atom, you substitute magnesium. And if you do this systematically, changing the composition from the center of the lens to the periphery of the lens, you can correct for chromatic aberration. That's what evolution has done. These nano-engineered lenses are just remarkable examples of the power of evolution. Okay, so what did we learn from mineral evolution the first 2 years? Well, Earth's near-surface mineralogy is diversified dramatically over 4.5 billion years. This evolution is characterized by a sequence of new mineral forming processes, and each of them explores new pressure, temperature, and composition regimes where different minerals can form. And of course, the biosphere, it turns out, has been a major factor in the diversity and the distribution of Earth's minerals. Those are all things we've learned. There's something else that's really important to me, and that's that mineral evolution represents a new framing of mineralogy for education and engagement. Now, I think back 65 years to when I was a young boy, moved to the New York City area, and for the first time I set foot in the American Museum of Natural History. This is the Morgan Hall of gems and minerals as it was back then. Row after row after row of minerals arranged by the Dana system, by their chemical composition and by their crystal structure. There's no story here. It's just one mineral after another, and I was mesmerized. I knew that I wanted to become a mineralogist. I was so excited by this. But this isn't really a way to engage most people. Most people are not just going to go to case after case and look at each mineral with a different chemical composition structure. Here is the new American Museum of Natural History Mineral Hall, opened just last year, and it's organized by mineral evolution. The hall tells a story, and the 5,000 specimens that are spread out before you, still mesmerizing, still beautiful, but they're part of a narrative. Every mineral plays a role in the drama of Earth's evolution. And to me, that's a very profound and exciting thing. And it's not just the American Museum. The Vienna Museum of Natural History had an exhibit in 2017, permanent exhibit in the Paris Museum. And next week, the opening of the Tucson Mineral Museum, which opens with the Mineral Evolution Gallery. So I'm very, very pleased and proud to see this becoming part of the narrative and also being used in teaching mineralogy. But as a scientist, think about this. Mineral evolution began as a qualitative narrative of Earth history with minerals in starring roles. But it's not rigorous, it's not quantitative. And so we kept saying, how can we make this more quantitative? Well, we need a quantitative approach by harnessing data, deep time data, and using the power of data-driven discovery. So this is part 2 of the story. This is the decade or so from 2010 to 2018. Now, what we did was we went to Bob Downs at the University of Arizona, my longtime friend and colleague, and he had been a heroic effort of building the RUF database. All the IMA-approved species are listed there. You can search by chemistry, you can search by structure, you can search by many other things. There's a huge amount of data on crystal structures and on optical properties and spectroscopy and so forth. So what we did is we added the evolution feature. You can click on this. And in that evolution feature, there are 200,000 mineral locality age data. This was a heroic effort of Josh Golden, who was a student there. We used an army of undergraduates. Alex Pyers helped do the coding for this. This was a huge effort, but now it's an open access resource. You can go and look at your favorite mineral and find out what ages are known for that mineral. We focused a lot on the first row transition elements. So these are things like iron and manganese and cobalt and chromium. They're very common in Earth's crust. They're economically important. Their behavior is often very sensitive to oxygen. So it tells us something about that evolution, and they play important roles in biology as well. So we basically made a plot. Here's a plot of 60,000 mineral locality age data. And on the horizontal scale, you'll see time going back 4 billion years, 4,000 million years, that is. And on the vertical scale, you'll see the numbers of mineral locality occurrences in 50 million year bins. And then the colors tell us something about the oxidation state. And boy, we learned a lot from this. There are 2 main takeaways. The first has to do with the supercontinent cycle. Over the last 2.5 billion years of Earth's history, Earth's continents have come together to form a supercontinent, as you see here, and then they've split apart, and then they come back together again. It's about a 400 or 500 million year cycle. There have been 5 major episodes. We can see evidence for that most clearly in the record of the mineral called zircon. Zircon is a common mineral that forms when igneous rocks magma cool and the zircon crystals form, and they're so resistant, they're so durable that they break apart when the rocks erode. They go into sand, and in sands all over the world you can find zircon crystals. You can date them, and you see 5 pulses of mineralogy corresponding to 5 episodes of supercontinent assembly. And the reason you see these pulses is when a supercontinent assembles, continents collide, mountain ranges are formed, and as mountain ranges form, new minerals occur in abundance. And also those mountain ranges preserve the minerals. So this is why we see these pulses. We see the exact same thing in our transition metal minerals, the same kinds of pulses. And the second feature that we see has to do with oxidation. So think about copper minerals. They're very important economically, but they also come in 3 different oxidation states. Most reduced is native copper, the metal. Most oxidized are those blue and green minerals like azurite and malachite. So my colleagues Shauna Morrison and Simone Runyon compiled a huge database of all the known copper minerals. They looked at all the different ages. And what they found is that the ratio of Cu2 plus to Cu1 plus increases very significantly, especially in the last 500 million years. So we can see evidence for Earth's oxidation in the minerals. We can plot these in all sorts of interesting ways. Here are all the first row transition elements plotted in the exact same way, and you can compare and contrast and see all sorts of details. There's a vast amount of information represented in this graph. And you can even go to the whole periodic table. You can go online to our website. You can click on your favorite element, and up comes the chart for that particular element. And you can see how those minerals are distributed through time. We can do another trick. This is really fun to me. This is using the platform of our University of Sydney colleagues called G-plates. They've reconstructed Earth's continents back 1 billion years. One of the reconstruction, which goes back 230 million years, you can put on your computer and you can plot where and when these different mineral occurrences happen. Yellow is copper minerals, black is uranium minerals in this particular case. And almost every case when you see a new dot pop up, it happens at the plate boundary. So we know that plate tectonics and mineralization are really closely tied. Okay, so this is the mineral evolution database, phase 2 of mineral evolution's evolution, if you will. And what we find is Earth's minerals display a striking episodicity in age correlated with supercontinent assembly. And one thing that's really important is that different chemical elements reveal significant differences in detail of these 5 supercontinents. It's not just one thing happening over and over again, but each supercontinent cycle has its own story to tell. And the minerals reveal those stories. Also, the redox sensitive elements, including these transition elements I just told you about, display increased oxidation state through time, as you'd expect because Earth became oxygenated. Though what's really interesting, we can also use the depth of formation of those minerals to see how the crust has been oxidized, not just the atmosphere, but we're talking about 1 kilometer or 2 kilometers beneath the surface where a lot of interesting processing occurs, and we can now document that through this process. So I think the MAD was a good first step. It's a quantitative approach, but it doesn't fully exploit the potential of mineral data. And so we've begun a new effort. And that's why I want to spend the rest of the lecture talking to you about the evolutionary system in mineralogy, which is based on mineral informatics. And what we're able to do is apply very powerful analytical visualization methods, and we use large and growing data resources. And here's sort of a key point. Minerals contain immense amounts of information. And you think about it, they have trace and minor elements, they have stable isotopes, dozens or hundreds of them. They have structural defects of all kinds. They have solid inclusions and fluid inclusions. They have sizes and shapes and physical properties and the context of the rocks in which they occur, all these different things. That's all data. So this leads us to part 3 of the mineral evolution story, starting in 2019 and going up till today. And every single day we're working hard on this. This is a really exciting ongoing project now. We need data resources. And so we rely on RUF. I've told you about that. There's also Jalion Ralph's incredible effort, mindat.org, that lists every mineral in all the localities in which it's known and all the coexisting minerals. That's really important. And then there's published sources, the Handbook of Mineralogy and Deerhausen-Zussman's Rock-Forming Minerals. These are multi-volume works. And of course, tens or hundreds of thousands of original articles. That's all data that we use. And these data resources are now introducing new analytical approaches. And so I want to take just a couple minutes to share with you some of these beautiful visualizations. Here's something called a chord diagram, extremely familiar in biology, never used in mineralogy before. And what you see here is a circle broken into segments. Each of those segments is a different cobalt-bearing mineral. These are the most common cobalt minerals that are found in ore deposits. By the way, cobalt is really important, and we've been studying it because it's part of battery technology, and it's a limited resource. People are trying to find new cobalt deposits. And this is one of the ways you can do that. And the chord, these curved, beautiful curved lines on this diagram represent pairs of coexisting minerals. And what you see is that some minerals are very, very commonly associated with each other's, whereas other minerals almost never occur with each other's. And that tells you something about formation environments. And this provides information in a visual format, a single visual format that would take just weeks and weeks pouring through lists of minerals and lists of data to see otherwise. Very powerful way of looking at mineral coexistence. Here's another kind of diagram, a clay diagram. And in this case, we're talking about a matrix that has 72 chemical elements on the vertical scale and 72 chemical elements on the horizontal scale. So what we're seeing here, coexisting pairs of chemical elements in minerals. And you'll see hotspots. Hotspots are these bright spots where the pair of elements exists far more frequently than you'd expect just from the average composition of Earth's crust. I've circled one. This is another cobalt example. It's cobalt minerals that also incorporate the element arsenic. And it turns out that pair is extremely common and quite surprisingly so. So we're trying to understand that, and this has been of great interest to people who do cobalt mineral exploration. And we can do the same trick now with a new visualization technique, a 3-dimensional clay diagram. This one 30 by 30 by 30, so 27,000 data points in this diagram, each one representing 3 coexisting chemical elements in a mineral. And when you see hotspots, it means those 3 minerals, those 3 elements are present much more frequently in the mineral kingdom than you might expect otherwise. So much, this could be a lifetime of study. And my favorite visualization, this is network diagrams. And here's a very, very simple one. You're all familiar with network diagrams, social networks of people who know people. Well, this is minerals who know minerals. And the minerals in this case happen to come from igneous rocks, things like granite and basalt. This was the very first network we made in 2016 with our friend Ahmed Alish at RPI. And what you see here are minerals connected to other minerals where they coexist in rocks, like granite. So granite is one subnetwork in this whole thing. There's basalt, there's something called nepheline cyanide, and indeed, all the igneous rocks are present in this one diagram. All the igneous petrology is embedded in this one simple diagram. And this really is a very simple diagram. I'll show you some more complex ones as we go along. For example, on the left here, chromium minerals. In this case, they're colored according to how they form. Orange is igneous minerals. Green, for example, are chromium minerals that form in weathered soils. And on the right, copper minerals colored by their chemicals. These, by the way, are called force-directed networks. Every mineral is sort of like linked by a spring, and so you can manipulate these. You can pull something. There's native copper on the left-hand side being pulled out, so you see what native copper is linked to. There's vast amounts of information that are embedded in these diagrams, and you can learn things about how minerals coexist that you'd never be able to understand otherwise. And you can do this. This is so much fun. I get such a kick out of this. This is a 3-dimensional diagram that Dan Hummer did for all the manganese minerals. And you see little pods of the one on the top there is a group of manganese minerals that form in granite pegmatites, and they seem to like each other, but they don't like anybody else. So they've got this own little separate, people that are sort of like that, or social cliques that are like that. Well, the same thing's true in the mineral world. Just amazing. And what's really fun, you should try this sometime. Here's Shauna Morrison doing a virtual reality, walking into that carbon mineral network. It's a bipartite network, 2 kinds of nodes, where the blue nodes are carbon minerals and the red nodes are the localities where those carbon minerals occur. Just astonishing amounts of information, and you can see patterns you'd never be able to see otherwise. So the key idea of this talk, we're going to exploit large and growing mineral data resources to develop an evolutionary system of mineralogy that reveals the coevolution of Earth and life. So what do we do in the evolutionary system? Well, we differ from the IMA protocols in 3 important ways. In some cases, we split an IMA species because it forms in multiple ways. In some cases, we lump a bunch of IMA species because they form in the same way. And we also include amorphous materials, things that are not crystals, because they play important roles in planetary evolution. Let me give you some examples. And diamond is one of my favorite. Diamond, IMA says it's pure carbon in the pure diamond crystal structure. But here's a diamond that formed maybe 5 billion years ago, before Earth even was a planet, in the atmosphere of a carbon-rich star. So that's stellar diamond. Then we have type 1 diamonds. They form in the mantle from a carbon-rich water-based fluid. We have type 2 diamonds that form in the mantle from a metal-based carbon fluid. Then we have impact diamonds, which form when an asteroid smushes a bunch of carbon to Earth's surface. You can think of an asteroid hitting a dinosaur and making a little diamond. That's kind of cool. And then there's this strange stuff called carbonado. It's been in the news a lot lately because there's a big, what they call black diamond. It's one of these things that's been cut and polished and weighs 555.55 carats exactly, and something mystical about that. But nobody knows where carbonados come from. They may be extraterrestrial, they may be formed in supernovas. We just simply don't know. So, but they're all different natural kinds of diamonds because they form in completely different ways. They have different trace and minor elements. They have different sizes and shapes and so forth. You can do the same thing with the mineral apatite. Very common mineral. It occurs in meteorites as little crystals. It occurs in glorious large crystals in some pegmatites, and it occurs in your teeth and bones. Yes, you have apatite throughout your body. And I would argue that the biomineralized apatite in your bones is quite different from the apatite that comes from pegmatites. The most natural kinds we've discovered for any one mineral is pyrite, known as fool's gold. That's an iron sulfide. It can form at very high temperatures. It can form at low temperatures. It can form with water. It can form without water. It can form abiotically, and it can form, as in the center bottom there, beautiful specimens that are formed by microbes. So pyrite has at least 21 different natural kinds. Now, in other cases, we lump species. So there are more than 30 species of the mineral group called tourmaline. You've probably seen tourmaline jewelry, and they can be so beautiful. And there's so many colors, but these crystals with these varied colors may have 4 or 5 different species in a single crystal. And we lump them together and say that's one kind because it's one crystal. This even goes down to the scale, the submicroscopic. I mean, here's Ed Grew's worked on very ancient tourmalines from Greenland and found that in single crystals that are less than a millimeter across, you can have a zoning so that there's one crystal in the center and one species in the center, another species on the outside. Once again, we call this one natural kind of tourmaline. And finally, we add amorphous materials, non-crystal materials, volcanic glass like obsidian used by our native indigenous people precursors. They use this for all sorts of tools and sharp objects. Coal, that's another important amorphous material, and other things, nanophases and mixed phase materials that just simply don't give X-ray diffraction patterns. I should note that Dana in 1850, he included all of these in his textbook because he thought they were important. But now that the IMA says you have to be a crystal, these are not included, but we do include them because they're important materials. And they may be extremely important in other worlds. The Curiosity rover on Mars has found that many sediments that we've analyzed contain up to 70% amorphous phases, non-crystalline phases. So if you just report the minerals that are crystals, that's 30% of what's there, and it doesn't give you a very good idea about the history of Mars's surface. Okay, so how do we do this? We have a bunch of papers, and one of the most important is now in press. It's called On the Perigenetic Modes of Minerals. There's also a companion paper we published back-to-back on lumping and splitting. And these papers, this really was my COVID stay-at-home project. So here's a spreadsheet. All this data science, all mineral informatics, it depends on data. It depends on spreadsheets like this. And this is an XLS spreadsheet that has about 5,700 rows, each representing a different mineral species. It has about 60 columns, each representing a different way that minerals form. And if you look in detail, so you can have a row like row 5 is taenite, that's the mineral, and it forms by perigenetic mode 1 and 3 and 4 and so forth. And there's lots of ones representing combinations of a formation mode and a mineral species. In fact, there's 10,556 ones in this spreadsheet, all done by hand, all done by looking through primary literature. It took many, many, many months, but it allows us to do things we couldn't do otherwise. It allows us to create this evolutionary system. So now let's look at the system itself. The first part was published in 2020. Part 1 is on stellar minerals, those minerals I told you about earlier. And what we do is we link a mineral like graphite, that's another form of carbon, with a particular environment, in this case, an exploding star called a type 2 supernova. Or there's moissanite, that's silicon carbide, linked to a very old star, an AGB star. Our sun will be an AGB star at some point and probably will produce moissanite at that point. And so what we do is we make a bipartite network to illustrate this. These graphs are courtesy of our colleague Anirudh Prabhu. He was at RPI before, but he's just joined us as a postdoc at Carnegie. We're so excited to have him working with us. And what you see then is 2 kinds of nodes. The ones that are shaped as stars are different kinds of stars. The ones that are shaped like little diamonds are different kinds of minerals. And every type of mineral is connected to one or more kind of star in this diagram, and every star is connected to one or more kind of mineral. And we can expand this, but I have to get into the weeds a little bit here, because this isn't something you just sort of toss off without thinking. There's a lot of work that goes behind a diagram like that. And I want to tell you about natural kind clustering. So how do we get silicon carbide and identify it from different kinds of stars? You start with meteorites. You have to dissolve them in acid, and you extract these tiny, tiny little mineral grains, some of them only a micron across. You then take your colleagues, Larry Nittler at Carnegie Science, but also Washington University in St. Louis, University of Chicago. They produced 17,000 isotopic analyses of silicon carbide. And you can take all those data and you can plot them up on different kinds of graphs, and you start seeing clusters of silicon carbide grains that are associated with supernovae or AGB stars or other kinds of stars. There's much more advanced ways of doing this. This is a paper that came out about a year ago, led by Asma Buyabar. And these are new cluster analysis results. So when I talk about AGB stars or type 2 supernovas, this is where those data are coming from, analyses like this. What we've learned from the stellar moissanite grains is that there's several different environments in AGB stars. They're very complicated. Also, we see supernovas and other kinds of stars, but most of the grains are coming from AGB stars. We've also done an analysis like this for pyrite, working with our friends at the University of Tasmania and University of Toronto. Dan Gregory's work has shown that there's 7 distinct kinds of pyrite based on different trace element patterns in ore bodies. And we've been building very large databases. By that, I mean hundreds of thousands of analyses of garnet and feldspar and spinel and other minerals. Those are in development. So this is a big part of what we're doing. It's very, very labor intensive. A lot of it's brute force, but that's what we have to do. Now, going back to the evolutionary system, part 2, published in 2020, looks at interstellar and solar nebula. And so you can expand that original graph. Here we're adding the earliest phases from the solar nebula. We can add interstellar clouds. These are very, very cold environments where you form different kinds of ices, water ice, but also CO2 ice and other kinds of things. We can expand this now to what we come to us in meteorites with the primary chondrule minerals. I told you about that. That was sort of part of stage 1. And here we see all sorts of new minerals with this stellar minerals still at the center, but those little nebula type arrangements in the outside. And parts 4 and 5 published just last year. Asteroids, where you have minerals formed through aqueous alteration, through thermal alteration, impacts. So you just keep expanding this diagram. It's really fun to see this sort of grow. Here's part 6, which was just accepted by American mineralogists. So it's in press. And here we see not just the meteorite minerals, which are shown in red and yellow on the left-hand side here, but also minerals that we think were present in Earth's earliest Hadean crust. Now, this is speculative because there are none of these minerals survive. There are no minerals from before 4.37 billion years, but we think we have very good reasons to suggest these minerals were present. And so early Earth minerals are in green and in yellow, and you see the yellow is the overlap. By the way, when you look at this, there's the original little network graph of stellar minerals. It kind of gets lost when you get to this level of detail, but they're still there, and they're still part of the network as we grow this larger and larger. And now take a deep breath, because we're going to jump to, oh, that's right. I almost forgot. We think this is the network that looks like Mars. We think Mars is very similar to early Earth. So we suspect there are not going to be a whole lot of minerals in this network that aren't in Mars. But what I was going to tell you, wow, look at this. This is 5,700 minerals in a bipartite network linked to about 60 different ways that minerals form. And it's colored. The green part on the right-hand side, those are all biological minerals. The red part in the upper left, that's igneous minerals formed in hot magma. And on the bottom, those blue fans, those are minerals that are formed through aqueous interaction. There's all different structures and components to this kind of diagram. We're learning so much. And I want to conclude by telling you some of our major mineral informatics conclusions to this point. One of the most important things we've discovered is that water is the principal driver of mineral diversification. More than 80%, and maybe it's closer to 90, depends on how you count them, of mineral species on Earth form through rock and water interactions in all kinds of environments, high temperature and low temperature, in the surface and also deep underground. And this means that if you have a planet that's dry, like Mercury or the moon, you just can't have a lot of mineral diversification because the water selects, concentrates, and distributes rare elements. A second really important finding is that biology plays a major role in mineral diversity, and here we can quantify it. Life mediates about half of all the known species. And of those, about 34%, that is more than a third of all mineral species, are exclusively formed through biology. If you don't have a living planet, you're not going to have the same mineral diversity that you see on Earth. A third really surprising discovery has to do with extremely rare elements. There are 41 rare mineral forming chemical elements, things like the rare earth elements, they're called, and the platinum group elements, and arsenic and molybdenum and some others. Collectively, those elements only represent 1 in every 10,000 crustal atoms. You pick up a handful of soil or pick up a rock, and only 1 in 10,000 atoms are going to be one of these 41 rare elements. And yet they are absolutely essential to 42% of the mineral species. Rare chemical elements have a disproportionate effect on the diversity. And I think this may tie back to the idea of water, because the only way you can select and concentrate these rare elements is to have water interacting with a rock. Over billions of years, you select, you concentrate elements, and then you can have local environments where these minerals can form. And finally, a hypothesis. This is something we want to test and continue thinking about. We're proposing that the diversity and distribution of minerals on Earth is in fact a planetary scale biosignature, and that the structure of this network diagram may in fact reveal something about life and its evolution. My final conclusion is that we've entered a new age of mineral informatics. We use multidimensional analysis and visualization of mineral systems, and this is leading us to insights about the coevolution of Earth and of life. With that, I thank you. I thank my many funding agencies, and I do hope there's time for some questions. I've enjoyed speaking to you tremendously. Thank you very much.
And thank you very much, Bob, for sharing your research with us this evening. It's truly amazing talk when you can go from Norman Bowen, who I hope everyone in the audience will know is one of Canada's most famous geologists, to clay diagrams, to diamonds, and somehow finish with a logical paper-by-paper history of our early solar system. And I know that many of you out there viewing our presentation tonight will have questions for our speaker. Please type them into the Q&A box at the bottom of your screen. And while we appreciate all of your questions, we might not be able to get to all of them. So we will do our best to get through all of the questions, and we'll group similar questions together as possible. I'm going to ask one of the first questions because it was something that piqued my interest towards the end of your talk there. I know that the folks working on Curiosity have done an incredible job describing the amorphous materials on Mars, but by definition, we're unable to characterize these materials by standard crystallographic techniques. So what are the ways forward as far as amorphous materials are concerned?
That's one of the biggest challenges, Ben, the characterization of amorphous materials on Mars. Mostly these days, they're doing it by saying what minerals are present. You know the bulk composition of your soil. You say, I've got 15% plagioclase, and I've got 5% of olivine, and I've got a bunch of clay minerals and so forth, and you know their rough compositions. You add all those together, you subtract them out, and whatever is left over, that's the composition of the amorphous material. Now, whether that amorphous material is a single gel-like material or glass or something else, could it be some of it volcanic glass? Should some of it be, gels that precipitate at the bottom of a cold acidic lake? We're not really sure. And so there's so much more to be done. But there are people who are working very, very hard on that process. And maybe 2 lectures from now, when Shauna Morrison talks to you about Curiosity, she may be able to give some insight on that as well.
Thank you. So our first question from the audience is from Juan Carlos de Obeso, who's a postdoc in my group, actually. And he asks, on the deep time analysis of minerals that shows increasing numbers of minerals and changes in oxidation state for transition metals through time, how do you control for the preservation if most of the old crust is gone?
Preservational bias, Juan Carlos, is one of the most difficult and important things for us to study. And we know there's preservational bias. For example, we do all kinds of systematic studies of parameters through time. And one of those, curiously, is the average hardness of the minerals through time. And if you look at the preserved minerals on Earth, the oldest minerals are the hardest minerals, and youngest minerals are the softest ones, which just shows that, we're losing soft minerals just through erosion and processes. So it is very, very possible that there are biases superimposed on our graphs. we know that's true in terms of just the absolute number of minerals. It may be true in terms of the character of the minerals, and the idea that, so we have to test, are redox, are more oxidized minerals softer on average? And I don't think that's true, but maybe it is. It's a hypothesis that's worth testing. And I will say one more thing about this. Every time I've talked about this to an audience, I get questions like Juan Carlos's that take us in new directions, because this is so new. This is so brand new. We just simply, so ask your questions, and there are no bad questions in this realm. We love new questions. Thank you.
Thank you very much. So the next one is from Dr. Rajiv Nair, who's a professor in our department. He says, thank you for the great talk. I think mineral evolution is a very neat concept, and kudos to you for springing this interesting field. And certainly understanding the habitats of mineral growth and evolution, which should be a worthwhile endeavor in geoscience. But I would argue that as a classification system, I don't think it meets the simplicity of chemical and structural classification. Certainly the information required to put them in an evolutionary context is very complex. And he would like to hear your thoughts on this issue.
I agree with Dr. Mayer 100%. We absolutely essentially need the IMA system. That simplicity, the fact that it uses the minimum bits of information, the fact that I can talk about, in this lecture today, I could talk about quartz and calcite and diamond and tourmaline. I couldn't do that if it weren't for the IMA system. And our system is unwieldy. It's incredibly complex. And I would argue that that messiness is exactly why it is a useful complement to the IMA system. That messiness itself, that information-rich messiness, is what gives us the opportunity to open up the time capsules that are contained with every mineral specimen. IMA doesn't allow you to do that, at least not in the formal classification. Every diamond is a diamond. But in our system, maybe there's 50 different kinds of diamond. That's messy. That's really tough. But on the other hand, maybe that's what nature is telling us.
Excellent. So as a response to that, Dr. David Pattison in our department has asked, how has the IMA reacted to your alternative system of mineralogy?
This, Dr. Pattison, that's I really appreciate that question. And I don't want to presuppose anything. I've been trying to be very cautious about in any way criticizing the system. And in my very first papers on this back in 2019, I was struggling. I knew that the IMA system was important, but at the same time I said, it just isn't doing it for me. I'm interested in the history of a planet. I'm interested in time. I'm interested in life. IMA doesn't allow me to do that. And so some of my comments, perhaps some of my published statements saying that IMA was, the system was, it failed to allow you to do something, we're not quite right. And there was one comment in American Mineralogist, and I replied to it, I hope in a humble enough way. But IMA just gave me their highest medal, which shocked me. It utterly shocked me, because I thought maybe I was a heretic. Maybe I was someone who was going to annoy some people. And yet there's a strange thing going on in mineralogy. I think that the IMA system, as powerful as it is, it's no longer leading to fundamental discoveries in physics and chemistry. We know X-ray diffraction, we know the periodic table, we know the space groups of minerals, we know about crystal chemical and crystal physical laws now, and it's very unlikely that discovery of new minerals is going to lead to fundamental new principles of chemistry and physics. But I do think discoveries in mineral evolution will lead to fundamental ideas about the evolution of our planet. And people recognize that. So the potential for discovery is really exciting at this point. And maybe that's why some people embrace the idea, even if it goes contrary to some of the IMA principles.
Great. So the next question I'm going to ask is from Tom Gallagher, who is one of the supporters of this lecture series. He says, can you say what the data can now say about water from mineral diagrams that you have made? When did water disappear? Sorry, I should have started this by saying he's talking about Mars. When did water disappear and what caused the magnetic field to disappear on Mars? And do you see this time in the evolution that stopped this evolution on Mars?
So first, I want to thank the Gallagher family so much for supporting this. It is such a generous thing to do, and the ability for some of us as scientists to communicate to such a broad and interesting audience, and and share our results is a real privilege, and I thank you for that. The history of Mars is a book that is gradually being deciphered. Mineralogy is playing a huge role, curiosity, perseverance, and of course, before that, spirit and opportunity. They were able to show us that clearly there was water, that the water disappeared billions of years ago, that there are remnants of it. There may still be places in the subsurface where there's some liquid water, but these are all things that are very, very active areas of study right now. Again, I'll point you to 2 lectures from now when Shauna Morrison will talk about some of the discoveries of curiosity and not just the mineralogy, but also understanding the evolution of Gale Crater, where it used to be a lake. It's very clear there's lake sediments. There used to be streams because we see sediments flowing in cobbles and stream beds and things like that. And now it's dry. And as it evaporated and as the remaining fluids became very acidic, it changed the mineralogy. So there's a lot of things we can understand about that evolutionary process, but there's much, much more that remains to be discovered. As to the magnetic field, that's another really fascinating area. I'm not an expert in it, but I know that it plays a key role in Mars's evolution and probably played a role in whether or not Mars could have supported life early on. So I'm waiting to hear more information on that as well.
Thank you for that. So I'm going to continue on the planetary theme by asking a question from Michael Spilde. Would you expect that there to be enhanced mineralogy on Titan, where the fluids are liquid hydrocarbons? Is water just extra special, or is the fluid phase also part of the magic?
Oh, Michael, I've actually been part of a couple of papers that talk about this Titan mineralogy and the mineral evolution of Titan. And you're absolutely right that the fluids on Titan are absolutely fascinating. Hydrocarbon, methane lakes, maybe ethane. The idea that evaporite minerals on Earth, when the Great Salt Lake evaporates, you get salt crystals. On Titan, when a lake evaporates, you get acetylene crystals. I mean, it's just crazy. And water is like a magma. Water is of course frozen at the surface, just like basalt is frozen at the surface of Earth, but it may be liquid deep within the planet, within the moon. So as water erupts, it forms, water volcanoes essentially, which rise into mounds and that's the rock at the surface of Titan. So you certainly have all kinds of interesting things going now. Whether the solvent methane acts like water to dissolve and then reprecipitate lots of interesting mineralogy, I would love to know that. Clearly, Titan has a different mineral evolution than Earth, and that is an important lesson, that there may be hundreds and hundreds of different evolutionary pathways for worlds of different sizes and different compositions.
Excellent. Thank you very much. So the next question I have is from Dr. E.F. Malone. Terrific talk. There are at least 2 ways for a supernova to form. I wonder if the binary source supernova gives rise to a different cluster of minerals than the massive single star supernova. Is there any way to tell?
So I'm not an astrophysicist, but my colleagues say yes, that there may be at least 3 different distinct populations of silicon carbide forming in different kinds of nova. And as I say, I'm not an expert. They told me about classic novas. They talk about binary novas. They talk about type 2 supernovas. And each of those has a different isotopic regime. And so if you form silicon carbide, formed from silicon and carbon, 2 very common elements, the isotopes of those elements can be very, very different depending on the environment in which the silicon carbide forms. And so people suspect they may have seen populations of silicon carbide, albeit very rare, much, much rarer than HEB stars, but they do seem to see different kinds of novas. And this also is a ground test for astrophysicists who model these processes, because part of their models is which isotopes are being formed in the stellar processes during the supernova eruption or before the explosions. And so if you actually have a grain that came, it's a physical object that came billions of years, in some cases before our solar system, and it formed in those environments, it just blows the mind. I just, every time I think about that. It astonishes me. So it's a great question. Thank you, Dr. Malone.
So another question from Kathleen Nestor. As you've been classifying and grouping minerals into their relative formation environments and periods, have there been any surprises or unexpected results that stood out to you that you'd like to talk about?
Oh, Kathleen, there's everything surprising to me. The number of minerals that are formed exclusively through biological processes, the number of incredibly rare minerals that form exclusively in only one environment. It turns out that more than half of all the mineral species only are known from a single environment. And so those are very quirky, rare minerals that form in idiosyncratic environments. And so I guess maybe the thing that I find most astonishing about Earth is how many different pressure, temperature, composition environments Earth has sustained for billions of years. And new ones keep popping up, for example, because of life.
So a question from Perrin Milliken, which I find it to be a really fascinating question. Thanks for the engaging talk. Minerals and materials are different. So does changing the categorization system mean changing what pyrite means, for example? Therefore, in your system, are there many more than 5,700 minerals, or are these just different materials?
Wow, Karen, that's such an interesting question. In our system, because of lumping and splitting, rather than 5,700 mineral species, there are only about 4,000 what we call root natural kinds, because we lump so many species of tourmaline, and we lump 30 species of eudialyte, and we lump many species of micas, and so forth and so on. So about 4,000, fewer than the number of species, but then each of those root kinds can be linked to a dozen or more different formation environments. And those are the natural kinds or the historical kinds in our system. I know it sounds a little complicated. It's complicated to us too. And we're still working it out. But the idea of first lumping and then splitting is fundamental to any classification scheme. Anytime you try to classify, people or I don't know, books or coins or whatever you're trying to classify, you have to do some lumping and some splitting. And so our system does that, starting, and essentially we're absolutely dependent on the IMA system. We couldn't do this without the IMA system.
Awesome answer to that question. So another question from Tom Gallagher, which I have only recently, due to my own naivety, realized is actually a very fascinating question. Do the moon rocks and rocks that we can go by, for example, launching another mission to the moon, Artemis, have a story to say about when they left the Earth system by a large impact? And is there something that we can learn about the evolution of minerals on our planet by looking at the moon?
Tom, it's one of my favorite questions. Going back to the moon, there are two things that are really important about the moon. First is the oldest rocks that we know of that aren't meteorites, that aren't things that came from before there were planets, are moon rocks. The moon solidified and crystallized about 4.4 or maybe a little more billion years ago. And other than lots and lots of meteorite and asteroid impacts, it hasn't weathered. So we can get very, very old rocks from the earliest period of the moon. And I think as a result, we have a better understanding of the moon's early mineral evolution than we do of Earth. But there's an even more important reason I want to go back to the moon, because we absolutely know that the surface of the moon is littered with Earth meteorites. Think about that. There were these epic collisions of asteroids and comets with Earth's surface, which flung some material all the way out of Earth, and some of those have landed on the moon, and they could easily be the oldest rocks that we'll ever be able to find from Earth. The oldest mineral grain that we found is 4.37, but the oldest rock is only maybe, if you believe it, about 4 billion years. And we want to know what happened in those first 500 million years of Earth history. That's a long time, 500 million years. So we really would like to get pieces of Earth from its first few million years. And I think the way to do it is to go to the moon and find these meteorites, they're not going to be common, but they're going to be there. And that's really an exciting opportunity. It's a good reason to go back to the moon, in my opinion.
I totally agree. And as I was referring to, my naivety was that I didn't realize that actually there's probably an abundance of very ancient rocks on the moon. So thank you for pointing that out. So the next question is from Andrew Masterson. This classification scheme is very data and computationally intensive, so it seems a natural evolution with the emergence of high-powered computers, virtual reality, etc. Have you applied AI, machine learning, or other machine-assisted analyses of these large data sets?
So this is really important, Andrew. The first major application of this, which I think is just going to take off and it's going to be taken over by the mining companies, is something called affinity analysis or association analysis. And that's using these very large data resources that we use. We haven't built them ourselves, of what minerals are found with what other minerals. And just like the way Amazon or Netflix, when you order a book from Amazon, it immediately comes back and says, if you like this book, you're probably going to like these other 5 books. Well, the way they do that is something called association analysis, or in their case, market basket analysis. And that's just a machine learning technique that basically looks at things that people like and things that people dislike, and has an algorithm that figures out what's likely. So we use that. We're also very eager to use machine learning AI type techniques to scan literature, to extract all of these mineral data from hundreds of thousands of PDFs that otherwise has to be done manually. And I'll make one comment about that also. Yes, it saves a huge amount of time for a machine to do that, but I have learned a huge amount about mineralogy that I never would have known otherwise by doing it brute force. Building that perigenetic mode database, mineral by mineral, paper by paper, day after day after day, for month upon month, just saturating myself with the world of minerals. I've seen things that I just couldn't possibly do if I let a computer do it for me. So that's to any of you out there who are interested in doing data science, you don't want to waste time, but sometimes going into the primary literature and seeing what it has to say with your own brain is not wasting time.
Excellent. So I have a nice question here from an anonymous attendee, and this made me think about my friend Sabin Zahirovich, who I saw in your talk there. This is a neat pattern recognition, gathering of information work. Truly, the collaborative effort is fantastic. However, I'm wondering if there are any theoretical efforts to create a framework more process-based rather than just a complex classification.
Well, I agree that would be really important. I think the most exciting theoretical work we're embarking on is I've just completed a detailed network of all the coexisting igneous minerals from 1,850 rock modes. Now, for those who aren't in the weeds here, a mode just means that someone has looked at a thin section of a rock and counted point by point, often 1,000 points, saying, what percentage of the volume of the rock is quartz or feldspar or pyroxene or an amphibole. And people did this mostly in a century ago. And there are tabulations, there are books that have this, and I basically extracted all this information. And now we have this database with 115 different igneous primary minerals, that is, minerals that formed right from the melt, in equilibrium assemblages in 1,850 rocks. And I think we can extract higher dimensional phase equilibria from the network graphs. We may even be able to extract thermochemical parameters, because people have done 3-component systems and 4-component systems for igneous rocks, but no one can go in and do a systematic survey of 8 or 10 component systems, but the rocks have done it for us. So we're working with Mark Ghiorso, who's well known in the field of theoretical thermochemistry of minerals, and trying to extract these higher dimensional phase diagrams from our work. So that's a kind of theoretical direction. If you're talking about a theoretical modeling of how an Earth should evolve, we haven't gotten there yet. Maybe someone will, maybe somebody listening today. I would love to see that happen.
Excellent. And I'm going to ask a question for Byron King here. I'm going to try to get it out right, although there's quite a bit of complex chemistry. Great talk. Thank you. Towards the end, you discussed rare earths, etc., and how small a measure they are in crustal abundance, yet how abundant they are in the minerals for which they are a part. In Byron's experience, with rare earths at least, the f orbitals seem to be the controlling features for the exotic magnetic, optical, and electronic properties. Could it be possible that those same f orbital electron properties have to do with concentrating the elements, and at least sufficient to become key contributors to mineral creation?
So Byron, I think the question about rare earths and all of those other elements is a crystal chemical one. As you well know, there are some rare elements like gallium, substitutes for aluminum. And so you never see, or you very rarely see high concentrations of that element because it just follows along with another element. But in the case of things like rare earth elements, in many cases, certainly the platinum group elements, molybdenum, there's no easy place where you can stick those atoms in a common rock forming mineral. And so as a rock begins to crystallize, the fluids become, the remaining fluids, usually water-based fluids, become richer and richer and richer in those odd elements. And only then do you start concentrating them enough to precipitate out minerals with those particular odd elements. It's not just that they're rare, it's their crystal chemical oddities. They don't easily fit into the crystal structure. So yes, the f orbitals play a very key role in the fact that they don't have a size and shape and a valence that easily fits in any common rock forming mineral. That's why you start getting all of these exotic rare earth minerals at the very last stages of crystallizing granite, or what are called agpiitic rocks, very high, or carbonatites. They're uncomfortable, and so they have to wait till they're sufficiently concentrated to form their own mineral.
Excellent. So the next question I'm going to ask is from Dr. Alan Hildebrand, another professor in our department. We saw on one of your plots, I think we saw the sort of age distribution of zircons through time. And how do the older dated zircons compare to the zircons of the 5 and per supercontinents, which is the figure that you showed? I think we saw Nuna and Rodinia, et cetera, on one of those figures.
Yeah, the older zircons, I know that there's some isotopic differences in them, and a lot of people like John Valley have studied this in great deal. I'm not an expert in that, Professor Hildebrand, but what I don't believe you see a systematic difference in the trace and minor elements in the zircons over the last 2.5 billion years. It's the isotopes from the very earliest zircons, and those are being used to probe the nature of perhaps the formation of the earliest vestiges of continental crust and the differentiation of the crust and mantle and so forth. So they're very, very important, but those are just traced. If you looked at the graph that I just showed you, they'd be such a minor blip at the extreme left end of that chart that you'd hardly even see them. But every one of those zircons that's more than 4 billion years old is precious and certainly deserving of intense study, as many people have been doing.
Excellent. So this is our final question for the evening from Jeffrey Tepper. And I quite like this as a concluding question, as we all ourselves go extinct, at least for the day. Do you ever see minerals go extinct?
Once in a while, a mineral can vanish from Earth. There are lots of ephemeral minerals that typically come back. All you need to do is see mineral extinction is not like life extinction. When a mineral goes extinct, you just need to recreate the conditions of temperature, pressure, and composition. One mineral that may very well go extinct in the next couple of centuries is ice. One can imagine a runaway greenhouse effect that melts every vestige of frozen water on Earth, but one would hope then at some point it would come back. There are other examples of mineral extinction. Venus, for example, very early on may have been quite habitable and may have had a whole range of hydroxides and clay minerals, but once it went to its runaway greenhouse effect, those minerals vanished. And the future Earth, when Sun becomes a red giant star and then turns into an AGB star, Earth will be blasted, lifeless on the surface. And once again, a lot of minerals that we now see on Earth's surface will be completely eliminated. So yeah, there are many scenarios. By the same token, humans are creating huge numbers of mineral-like compounds, and if we go away, those minerals may preserve for billions of years and form a marker layer, which indicates that we were here, even if we're long gone.
Thank you very much. And thank you everyone out there for your questions tonight. It's been a pleasure being with you here tonight and being able to participate in this Gallagher presentation. I'm going to now turn it over to Stephen Hubbard for closing remarks.
Hi, everyone. Thanks for being here. And I'd just really like to start by thanking Bob on behalf of the Department of Geoscience, Dean Bates, and the entire Faculty of Science for joining us this evening to present about your research. What a fascinating talk. I kind of at a loss for words a little bit. The narrative you spun, just the fascinating tales that you communicated, it somehow brought me back to that feeling I had as a young student in geoscience. It really was a moving presentation, and I hope and expect that others in the audience felt that too. Before you all leave today, I do want to remind you that our Gallagher Colloquium series will return in March with 2 events. On Thursday, March 3rd, Dr. Bob White, senior geophysicist from the Geological Survey of Canada, will be discussing geological storage of carbon and the role of geophysics. On Wednesday, March 30th, we welcome research scientist Dr. Shauna Morrison. Dr. Morrison is also from the Carnegie Institute for Science, and her presentation is titled Driving Curiosity, Exploring Martian Geology in Habitability through Mineralogy. So it should be another fantastic presentation. If you haven't been receiving our emails about this series and would like to subscribe, please do email us, scialumni@ucalgary.ca. For links to all the items that have just been mentioned, please see the chat box at the bottom of your screen. We've also shared the link to our faculty's donate page. While we receive our core funding from the provincial government, much of the extra support for our students and researchers or events like this one are made possible through individual and corporate gifts. Gifts of $10, even $20, they add up quickly and make a real impact. So please consider the option. And then lastly, when you do see our event survey in your inbox, please take a moment to fill it out. Your feedback is important and we want to hear from you. Again, thank you for coming. Enjoy the rest of your evening.